Hello and welcome to my YouTube channel or the Big Structural Hub. This is the #1 channel for structural insight. Today I want to solve two problems. Number one is for slab and number two is for a beam. So for slab, I will be solving the last question under a simply supported slab. A simply supported slab is a slab resting on two supports, as you can see on the board. So let's tackle this question first for a slab, and then we proceed for a beam. So the question is on the board and it reads, a concrete floor reinforced with 10 mm diameter milled steel bar Fy is equal to 240 Newton per millimeter square at 150 mm centers. Area of steel is equal to 628 mm square per meter width of the slab between brick walls as shown below. Calculate the maximum uniformly distributed imposed load the floor can carry. So this is the section. The thickness of the slab is 150. So this is the overall H. And the center to center distance between these two walls is 3000 millimeter. And the thickness of the wall is 150 millimeter. So we will use FCU as 30 Newton per millimeter square and the unit weight of concrete as 24 kilonewton per meter cubic and the cover as 30 millimeter. So let's see how we can solve such a question. So solution, before I begin solving this question, I want to capture the most important information on this column so that I can rub here and create more space for more calculation. So the diameter is 10 millimeter. So diameter 10 millimeter. The area of the steel is equal to 628 millimeter square, and the steel distance from the center of one steel to the center of another steel is 125 millimeter. So center to center distance of the steel 125 millimeter. Fy 240 Newton per millimeter square, and then the thickness of the slab is 150. So slab thickness is equal to 150 millimeter, and the wall is equal to 150 millimeter. Center to center distance between these two walls is equal to, so center to center distance of the two walls is equal to 3000 millimeter. So this is walls, and FCU is equal to 30 Newton per millimeter square. Unit weight of concrete is equal to 24 kilonewton per meter cubic. Cover is equal to 30 millimeter. So by doing so, I can comfortably rub here so that we can continue solving our problem. So solution, the first thing to do is to calculate the effective depth. So D is equal to h minus cover minus a half of the diameter. So this one is equal to, our h is 150, cover is 25, and the diameter is 10/2. So which imply D is equal to 120 millimeter. So maybe I can draw for you a sketch to differentiate between a D and a H. So if this is a slab, and this is the cover, which is 25, and this is the steel, so this is the steel, 10 millimeter. So D is this distance from the top of this steel, from the compression side to the center of this diameter. So this is D, and this is H. So to get D is equal to cover is equal to H minus cover minus diameter divided by 2. This is diameter 10, you divide by 2. So this one is equal to 150, H, cover is 25, and then diameter is 10/2. You will get 120 millimeter. So this is our D. We now proceed to effective span. Effective span. So effective span should be lesser of the two. So this one should be lesser of A. You have the center to center distance between two walls, center to center distance between two walls. So this one is equal to 3000 millimeter. Maybe I can draw a sketch to illustrate on this. So if this is a slab, so this is our slab. So the center to center distance is 3000, as you have seen in the question, and the wall thickness is 150 millimeter. So the effective span should be lesser of A, center to center distance between two walls, as you can see, 3000, and B, clear distance, plus D. So clear distance is this distance, the internal distance between the wall. So this internal distance between these two walls is given by 3000 minus a half of this wall and also a half of this wall. So the wall thickness is 150. So a half of 150 is 75. 75 times 2 is 150, which imply clear distance is equal to 2850 millimeter. So this one is equal to 2850 plus D, which is 120 millimeter. So this one is equal to, if you add, you will get 2970 millimeter. So therefore, effective span is equal to 2970 millimeter, which is lesser. So after that, we proceed to loading. We now proceed to loading. So let's continue. So loading, we have loading. Under loading, we have the dead load. So we have the dead load, which is GK. So this is the load, the self weight of the slab plus any other load which is permanent on the slab. It can be finishes, etc. So since we don't have any other load, we'll just calculate the self weight of the slab, which is given by, so the slab thickness is 150. You divide by 1,000. When you divide by 1,000, it means you are converting from millimeter to meter. So this one will be in meter. Then times the unit weight of concrete, which is 24. So times 24 kilonewton per meter cubic. So meter will cancel with this meter cubic. So this one is equal to 3.6 kilonewton per meter square. Then the imposed load. So this is what we are looking for. So we'll say let imposed load to be QK, like that. So the design ultimate load, ultimate design load is equal to 1.4 GK plus 1.6 QK times 1 meter width of the slab. So this one is equal to 1.4 times 3.6 plus 1.6 QK. Remember the unit is in kilonewton per meter square times 1 meter. So this one will go here, meter. Then we will remain with, no, let's carry out the operation. So 1.4 times 3.6, 1.4 times 3.6. So this is 5.04. 5.04 plus 1.6 QK. K. So this is kilonewton per meter. So this is the design ultimate load. After this, we now proceed to the ultimate design moment. So the ultimate design moment will be given by WL squared over 8. So if this is our slab, a simply supported slab, and the effective span, as you have seen, is 2970, which is 2.970 meters, and the loading is 5.04 plus 1.6 QK. This one is in kilonewton per meter. Therefore, it means the ultimate design moment, which is M, will be given by WL squared over 8. So M is equal to WL squared over 8. So our W is 5.04 plus 1.6 QK times L, which is 2.970 square over 8. Let's open the bracket. So to open the bracket, you take 5.04 times 2.970 square, then you divide by 8. So you'll get 5.557 plus 1.6 times 2.970 square over 8. You will get 1.764 QK. And remember, this is in kilonewton meter. So this is our M, like that. After doing so, the next thing to do is to write the formula for area of steel. So you know that the area of steel is given by M over 0.87 FYZ. And this M is what we have here. So we can make M the subject of the formula. So M is equal to, so you'll cross multiply area of steel times 0.87 FYZ. And since we don't have M, we will assume Z. So assume Z is equal to 0.95D. So this one is equal to, so which imply Z is equal to 0.95 times 120. So this one is equal to 114 millimeter. So that is our Z. So M is equal to area of steel is this one, 628 times 0.87. Fy is this one, 240 times times Z, which is 114, like that. So let's carry out the operation. So if you carry out the operation for this, you will get your answer in Newton millimeter, but we want our answer in kilonewton meter. So you'll multiply by 10 raised power negative 6. So this one is equal to 14.948 kilonewton meter. So to get the imposed load, which is QK, we will equate this moment to this one, and we will get our QK. So let's equate these two values to get, so that it can help us to get the QK. So 14.948 is equal to 5.557 plus 1.764 QK. So 14.948 minus this one will cross to this side, so it will change from positive to negative. 5.557 is equal to 1.764 QK. So 14.948 minus 5.557, so it's equal to 1.764 QK is equal to 9.391. So to get QK, you divide both sides by 1.764, 1.764, which imply QK is equal to 5.32. This is in kilonewton per meter. So remember, we assumed our Z. So after having calculated this, we can now check if the value we assumed for Z is correct or not. So lever arm, which is Z, so you know that Z is equal to So this is the formula to get the value of Z, whereby K is equal to M over FCU BD square. So K is equal to M, which is 14.948 times 10 raised power 6. You change it from kilonewton meter to Newton millimeter over FCU. FCU here is 30 times B. Remember, B is the 1 meter width of the slab. So this is 1,000 times D, 120 square. So this one is equal to 14.948 times 10 raised power 6 over 30 times 1,000 times 120 square. So this one is equal to 0.0346. So Z is equal to D, 120 so which imply Z is equal to Z is equal to 115 millimeter. It therefore our Z assumed, which was 114 millimeter, is the correct Z. So therefore, hence assumed value of Z is the correct, and the maximum distributed load that the floor can carry is equal to 5.32 kilonewton per meter. So therefore Z assumed is correct, and QK is equal to 5.32 kilonewton per meter. So that marks the end of this question, and we proceed to a question for a beam. So I told you today I will solve two questions, that is for a slab and for a beam. So let's proceed to a beam. So question number 2 is this on the board, and it is beam designed to BS 8110. The question is from past paper, July 2023. It is question B. I think it is question 3B, and it carries 16 marks. So I will read the question. Design a simply supported rectangular beam for bending and shear. Use the following information. Overall depth of the beam, 600 millimeter. Breadth of beam, 300 millimeter. Clear span of beam, 4850 millimeter. Breadth of supporting column, 150 millimeter. FCU, 35 Newton per millimeter square. The strength of the main steel is equal to 460 Newton per millimeter square, and the strength of the shear steel is equal to 250 Newton per millimeter square. So dead load is equal to 25 kilonewton per meter, exclusive of self weight. imposed load is equal to 20 kilonewton per meter. Provide T 25 for main reinforcement and R10 for shear reinforcement. Exposure condition is mild. So let's see how we can tackle such a question. Again, I want to write here the information that will help us in calculating or in solving this problem, and then I will clean here so that I can have more space for more calculation. So overall depth of the beam is 300 millimeter and the breadth of the beam is 300 millimeter. So if I draw the section, this is how it will look like. So the H is 600 and the B is 300, like that. So the clear span is 4850. So the clear span is 4850. So again, if I can draw the section of this beam, this is how it will look like. So this is the clear span, which is 4850. So 4.85. So this is the column. This is the two column. So the breadth of the column is 150. So the column is 150. Like that. And remember again, our H is 600. So that is our H. Again, FCU is equal to 35. FY is equal to 460. FYV is equal to 240. So the dead load GK is equal to 25 exclusive self weight. So exclusive self weight. And then you have the imposed load QK is equal to 20 kilonewton per meter. Also this one kilonewton per meter. T25 for main reinforcement, T25. This is main, and R10 shear, R10 shear, and then exposure is milled, so cover is milled like that. So I can comfortably rub here so that we can continue with our calculation. So solution. So to begin, we start by the effective depth of the beam, which is D. So D. So to get D, if I can draw here the section of this beam, so this is the beam with reinforcement. So the overall depth is 600 and the B is 300. So the D will be this distance from the top of combination side to the center of the main diameter. So this is the link, which is equal to 10 millimeter, as we have been told in the question. And this is the main bar, which is 25 millimeter diameter. So to calculate D, so D is equal to H minus cover, and this is the cover, minus cover, minus the diameter of the link, minus the main diameter divided by 2. No, the main steel divided by 2. So this one is equal to H is 600 minus cover. So we have been told the exposure is milled. So this one, the value for this is given in table 3.4 of BS 8110. This table provides cover for reinforcement of column, beams, and the slabs. So for milled, it is 20 millimeter or a bar diameter, whichever is greater. So for milled, it is either 20 or the diameter of the bar, whichever is greater. So you have been told that main diameter is 25. So if you compare 20 and 25, automatically 25 is greater. So we will use 25 as cover. So minus 25 minus diameter of the link, this is 10, minus main bar, which is 25 over 2. Therefore, D is equal to, so D is equal to 552.5. So let's say 553 millimeter. So this is our D. We now proceed to loading. So loading, so we have the dead load, which is GK. GK is equal to 25 kilonewton per meter plus self weight of the beam. Self weight of the beam. Because in the question, we were told that 25, which is the dead load, it is exclusive self weight of the beam. So we have to include the self weight of the beam. So to calculate self weight of the beam is equal to, you take the cross section area of this. So this one will be 0.3 times 0.6. 0.3 times 0.6. We have changed from millimeter to meters. So 300 will be 0.3 and 600 will be 0.6. So this one is equal to 0.18 meter square. So self weight, it will be 0.18 meter square times the unit weight of the concrete. Since we have not been given the unit weight, we will assume the unit weight as 24 kilonewton per meter cubic. So here it will cancel with this. So if you multiply, you will get 0.18 times 24. So this is 4.32 kilonewton per meter. So the GK is equal to 25 plus 4.32, which is equal to 29.32 kilonewton per meter. So that is our GK. So and our QK is 20 kilonewton per meter. Therefore, we can now calculate our ultimate load. Ultimate design load. So ultimate design load is equal to 1.4 GK plus 1.6 QK. So this one is equal to 1.4 times 29.32 plus 1.6 times QK, which is 20. So this one is in kilonewton per meter. So let's carry out the operation. So this one is equal to 73.05 kilonewton per meter. So if this is our beam, So this is the loading on the beam. This is 73.05. And then you have the effective span. Effective span is 4.85 meters. So you can now calculate the ultimate design moment. So for a beam, don't be confused a beam and a slab. For a beam, there is no, we will not calculate the effective span as the lesser of the two. So you just take the effective span the way it is, or the way you have been given in the question. Like here, we have 4.85 meters. And the effective span is the distance between the center of the two columns. So this is a column, and this is a column. So the ultimate design moment, which is M, is equal to WL square over 8. So which imply M is equal to 73.05, this is in kilonewton per meter, times 4.85 square over 8. So this one is equal to, let's carry out the operation. So this one is equal to 214.79 kilonewton meter. After calculating the ultimate design moment, we now calculate the moment of resistance. So Mu is equal to 0.156 FCU BD square. So this one is equal to 0.156 times FCU is here, 35. B, our B here is 300 times D. Our D we have already calculated, 553 square times 10 to the power negative 6. So that you can get our answer in kilonewton meter. So this one is equal to 501 kilonewton meter. So since M is less than Mu, no compression, reinforcement is needed. So we will only design for tension only. So let's determine the area of steel. So the area of steel is equal to M over 0.87 FYZ, whereby Z is equal to and K is equal to M FCU BD square. So K is equal to Our M is 214.79 times 10 raised power 6 over FCU is 35 times B is 300 and D is 553 square. So K is equal to 0.0669. This is the value of K. So Z is equal to 553 which imply Z is equal to, again you punch your calculator, so Z is equal to 508 millimeter. And remember, Z should be less or equal to 0.95 D. So 0.95 times 553 is equal to 0.95 times 553. So this one is equal to 525 millimeter. Therefore, use Z as 508 millimeter. So this is our Z, 508 millimeter. We now proceed to the area of steel. So this is the formula for the area of steel. So is equal to the moment is equal to 214.79 times 10 raised power 6 over 0.87 Fy. Fy is this one, 460 times Z, 508. So which imply S is equal to, I have multiplied this moment by 10 to the power of 6 to change from kilonewton meter to Newton millimeter. So the area of steel is equal to 1057 millimeter square. So provide as you have been told in the question, use T25 for main reinforcement. So provide 3T25 and the area of steel is equal to 1473 millimeter square. So I assume you know how to convert this area into steel, into the number of steel and the size of the bar. but I will show you how to do it. For those who have been following my content, I'm very sure you know how to do it. So this is the table. As you can see, you have the bar size and the number of bars. The number of bars, we have 1, 2, 3, up to 10. So the bar size, as we have been told in the question, to use T25, so you will come where 25 is and select an area which is higher than this, slightly higher than this. So, but since the table in your exam is different from the one I'm using, so this one I obtained using the table provided in your exam, but there is a small difference with the one I'm using. So 25, for this one, the area is 1470, but for the one in your exam is 1473. So this is how you convert this area into the number of bars and the size of the bar. So this is a cross section for the beam we have designed. So as you can see, this is the main reinforcement, which is 3T, 25 millimeter in diameter. And this is the link. So link is R10. And we have the bar at the top. This one is, we call them a hanger bars. So they are provided to hold this bar, the main bar, in place and to connect together with the link. So this is the H 600 millimeter, B is 300 millimeter, and the D is 553. We now proceed to shear reinforcement. So shear, so this was our beam. And the loading is 73.05 kilonewton per meter. So the effective span is 4.850 meters. So this is A, B. So this is R A, R B. So the design or the maximum shear, which is capital V, is equal to WL over 2, which is equal to RA, which is equal to RB, RA and RB. So this one is equal to 73.05 times 4.85 over 2. So this one is equal to 177.15 kilonewton. So if we can draw the shear force diagram, this is how the shear force diagram will appear on this beam. So this is 177.15 and also 177.15, like that. This is positive, this is negative. So the shear stress, which is small v, is equal to V over BD, which imply V is equal to 177.15 times 10 raised power 3 over B, which is 300 times 553. So this one is equal to 1.07 Newton per millimeter square. And this one should be less. So V should be less 0.85 square root of FCU. So 0.8, no, it's 0.8, not 0.85, 0.8 square root of 35 is equal to so it's equal to 4.7. Therefore, K. So VC, the maximum shear stress in the concrete, is given or is calculated using this formula, 100 AS over PD. So this one is equal to 100 AS is the area of steel provided, which is 1470. Yes, which is 1473. 1473 over B. B is 300 times D, which is 553. So this one is equal to 0.888. So you take this value into a table of VC, and this table will give you a VC for class 25 of concrete. And then to get the VC for class 25, you will take that 5 over 25 times the value obtained in this table, and you will get the VC of class 25. So this table will assist you to get a VC for FCU 25 Newton per millimeter square concrete. So our value, which was obtained from 100 AS over BD, is 0.89. 0.89. So as you can see on this table, we have a column of 100 AS over BD, and then the effective depth D, which is in millimeter. So our value, which is 0.89, is not on these values provided in this column. So which means we are going to interpolate to get a value of 0.89. So we'll go for a value which is slightly lower than 0.89, which is 0.875, and proceed to our D, which is above 400 millimeter. As you can see, these are the value for D above 400 millimeter. So this is 0.57, and a value which is higher than 0.89 is 1.0, and we have 0.63 for this column. So this is 0.63, and then we will interpolate to get our X. So if you get the difference between these two, and this, so you'll have 1.0 minus 0.75, then over 0.63 minus 0.57, and then you equate to the difference of these two, which is 0.89 minus 0.75 over x, of which you don't know. Then you make x the subject of the formula, which imply x is equal to 0.0336. So I have skipped that and go direct to the answer, which is 0.0336. Then VC for 25, it will be 0.57 plus 0.0336, so which is equal to 0.6036 Newton per millimeter square. So this is for VC. This VC is for class 25. So to get VC for class 35, you will take 35 over 25 raised power a third times the value of VC, which is 0.6036. So you will get 0.68 Newton per millimeter square. So 0.5 VC is less than V, and V is less than VC plus 0.4. So this is 0.34 is less than V, which is 1.07, and less than 1.08. So VC is 0.68 plus 0.4. This one is equal to 1.08. And 0.5 times VC, which is 0.68, you will get 0.34. Therefore, provide minimum reinforcement, provide minimum shear reinforcement in the entire beam. So let's now calculate the spacing and the area of the shear reinforcement. So use this equation to calculate the value, to get the value which will give you the area of the reinforcement of the link and the spacing. So this one is equal to 0.4 times B, which is 300, over 0.87. FYV is 250. So this one is equal to 0.552. 0.552. And then let's now obtain the size of the shear reinforcement links and the spacing using 0.552. So therefore, provide R10 at 250 millimeter center to center, then ASV over SV is equal to 0.571. So this is how you read it from the table. So this is table 3.13. As you can see, you have the column for diameter in millimeter 8, 10, 12, and 16. And then you have the spacing. So our value there is 0.552. So you'll come to our 10 as we have been told in the question and look for a value that is slightly higher than 0.552. So that is 0.571. So it is at 10 at 275 millimeter center to center. So this marks the end of the two questions, and I hope umepata kitu. So next time in my coming session, I will be tackling continuous one-way slab. So what we have been doing is a simply supported a slab, and as from next week, I will begin continuous one-way slab, plus some other examples from past papers for beam. So stay tuned for that. And if you have not subscribed to the channel, please subscribe and hit that notification bell so that you may be the first person to be notified when a video is uploaded. So thank you for your time, and we meet again in my coming session.